below the water table, we know that that is called groundwater. Okay, in groundwater, basically all the pores, all the interstices are filled with water. Okay, and from this zone only we can tap water. So from the quantitative, if I want for withdrawals and all, this is the water, this is the zone which really gives water. But above this, we know, okay, that there is a what we call it as unsaturated zone or vadose zone, which extends from the ground surface to the water table. Okay, so this zone is okay. So you have the groundwater table here, and you have the starting from the soil surface to the water table. We call it as the vadose zone. Okay, where here the main characteristics of this zone is that here you will have it is not fully saturated. That means the soil voids are not really totally filled with water. So some voids are filled with water and some with air. Okay. So basically that's why it's called. So obviously the moisture content or how we define as we take a sample of soil. Okay. Whatever is the volume of water is available in that sample divided by the volume of the sample, we call it as the moisture content. Okay. So in this moisture content, obviously will be equal to porosity in the saturated zone because all the pores are filled with water here. But whereas here, the moisture content, usually we denote it by theta, so that will be less than or equal to, okay, in the capillary chain, okay. So basically, and another important characteristics of this zone is that, okay, the pressures, the water pressures are negative in this zone, whereas in the saturated zone, okay, below the groundwater table, you have pressures, positive pressures, okay, whereas in the unsaturated zone, the water pressures are negative. Okay, that's why if we want to measure the pressures in the unsaturated zone, you cannot use piezometers. Okay, we need to use some other way of. Usually, we have what we call it as the tensiometers. Basically, here the water in the unsaturated zone is usually held due to the capillary forces. Okay, so basically the soil here has the tendency to take more water because it is not fully saturated. Okay, so these tensiometers basically they try to see how much water I can give it to the soil. So that gives at what tension this, what negative pressure this. Okay, so this vadose again we can characterize it into two main zones. One we call it as the root zone. Okay, where the root activities are more because all the crops. Okay, usually the crops, the major crops which we grow. Okay, so they have their roots. Usually their length is around 1 to 1.5 meters, maximum 1.5 meters. So the top 1.5, usually we call it as the root zone, where the root activities are very, very active. Okay, but below that, we call it as the vadose zone or the unsaturated zone, where the soil moisture movement is not that much affected by the roots. Okay, so this is what a main characteristic. And one more characteristics of this unsaturated zone is that, okay, the soil properties, okay, like the hydraulic conductivity. So let us say, I have a homogeneous and isotropic soil, okay, from throughout, okay. Even so, below the in the saturated zone, given the soil type, we can take the soil properties like hydraulic conductivity or the storage coefficient or specific yield, they will be constant. But whereas here, okay, even if the soil is homogeneous, the hydraulic conductivity is not only a function of the type of soil, but it also depends on what saturation it is. Okay, so it's basically a time dependent value. Okay, even for a homogeneous soil, but whereas here it is constant. So that's why the dynamics of water movement in the soil in the unsaturated zone is much more difficult and makes the governing equations non-linear. Okay, just because the pressures, the soil properties, they not only depend upon this type of soil, but they also depend upon the at what pressures it is there. Okay, so K is not only a function of the soil, but is also a function of the pressure. Okay, so that's why it's much more difficult to base. So the main, if I want to analyze problems involving flow of water to unsaturated zones, okay. So basically, we know that the pressures are negative in the unsaturated zone, and for each of these negative pressures, you will have a different moisture content. That means if the soil is dry, okay, so the moisture content will be less or more. It will be less, and the corresponding soil pressure, okay, will be very, very high in negatively. Okay, so usually we call this as the suction pressure. Okay, if I call suction pressure, I use positive. If I use pressure, then we will be using negative values because the pressures are less than atmospheric in the unsaturated. So basically, if we want to analyze problems involving unsaturated zone, okay, we need to know what is the relationship, how the moisture content changes with pressure, with the negative pressures. This is called what we call it as the soil moisture characteristics or capillary pressure saturation curves. Okay, so a typical if you see here, a typical soil moisture content looks like this. So this is -10, that means basically we are very near to saturation. Okay, the corresponding moisture content will be very high. Okay, for different types of soils, you will have different. So as I increase the negative pressure, okay, that means as the soil becomes dry and dry, okay, so the moisture content will come down, okay, and you will have this. Okay, so this is a typical soil moisture. It looks like a we can say a S curve. Okay, and there is one more. We can know what is capillary fringe. Capillary fringe is that portion above the water table where the pressures are negative, but the moisture content is more or less equal to porosity. Okay, it's more or less saturated. Okay, so it requires certain amount of pressure for the air to the moment the soil becomes unsaturated. That means some air has to go in. Then only it becomes unsaturated. So what is the pressure at which the air will enter the soil? Okay, that pressure is called the bubbling pressure. Okay, so this bubbling pressure will be high for which type of soils? Let us say I have a soil which is sand and which is clay. So where do we need? We have to exert more pressure to send air into the soil. In clay. So that's why. So the bubbling pressure will be very high. Okay, for clays. That's why the capillary fringe thickness will be very high for clays as compared to, because the pore size is very, very small. Okay, you need to exert more pressure. Okay, to send water. Okay, so these soil moisture characteristics are very much necessary for us to analyze flow through the unsaturated zone. So they are also called soil moisture retention curves. Okay, so many names are there. So a typical soil moisture content curve looks like this. Okay, and so as I have already explained, the soil water content, if you see here, so many researchers have worked on how these characteristics look like. Okay, and many researchers have given their relationships. Okay, they have conducted a lot of experiments on different types of soils. Okay, starting from with a saturated soil sample, they try to dry it out and get the suction pressure and plot, and they try to fit some curves. Okay, so that they can we can use this relationship for solving moisture movement problems in the unsaturated. So the the most prominent of these uh, characteristics are given by the first one was very popular before Brooks and Corey. They gave this in 1964. Okay, so where you can see that the theta is basically the moisture content here. Theta R is the residual moisture content. Phi is the porosity. Theta R is again the moisture. Is related to the suction pressure or the pressure head H here. H is the pressure head. This HB is what we call it as the bubbling carburation pressure. Bubbling pressure means the pressure at which the air will start entering the soil. It requires certain pressure for the air to to enter into the soil. So they have given this. This was a very popular uh, relationship which has been used by many researchers. Okay, but the only problem with this that this is not continuous because this is valid only for pressures less than HB. Okay, for pressures between 0 and HB, usually this is not valid. So that's why it has some limitations, but still it was a very it's very well known equation. It has been widely used. Okay, and also if I have to solve problems with unsaturated fuel, we also need the hydraulic conductivity. As I told, okay, the hydraulic conductivity in unsaturated zone is not only a function of the soil, okay, it is also a function of saturation or pressure head. So they have also proposed a relationship, this k theta divided by kl. Basically, this kl is nothing but the saturated hydraulic conductivity, which we take it for saturated zone. Okay, so and this unsaturated hydraulic conductivity k theta, okay, is always less than the saturated hydraulic conductivity. Usually we put it as a fraction of, okay, the saturated hydraulic conductivity. That fraction depends upon how much is the water content in the soil. If the soil is very dry, the unsaturated hydraulic conductivity will be less, okay, because the water has to take longer paths because you have more water, air in that. So that's why that will be less. As the water, as the soil gets wetter and wetter, this unsaturated hydraulic conductivity also increases, and when it becomes fully saturated, it becomes equal to the saturated hydraulic conductivity. Okay, so this is one which was given by Brooks and Corey in 1964, and there were some improvements. Campbell has improved it again, but still it has this bubbling pressure here, HB. Okay, and in 1980, this Van Geneten, okay, he proposed a relationship between theta. Theta is the moisture content, and H is the pressure head. Okay, so which is valid even for pressures less than bubbling pressure also. That means it can be used from 0 to minus any suction pressures. Okay, there is, so this is, and nowadays this is the most widely used soil moisture characteristic relationship in most of the problems involving flow through Vadosjor or flow through unsaturated. Basically here also we have theta as a moisture content. Theta or we call it as a residual moisture content, at which basically it is not wilting point. It is the residual moisture content at which it is the moisture content at which the hydraulic conductivity becomes zero. Very, very, very dry. Okay. And phi is the porosity, and this alpha and n. Okay. These are the parameters. We call it as the soil retention parameters, alpha and n. Okay. They depend upon the type of soil. Okay. So for different types of soils, you will have different different alpha and n. Usually, physically, this alpha, okay, is basically an inverse of the bubbling pressure. This alpha will have a unit 1 over L, okay, and this basically physically this gives you, this quantifies a more or less what is the bubbling pressure. If I take the reciprocal of alpha, that gives me bubbling pressure. Okay, and this N depends upon how these pores are, okay, organ and the pore structure. Okay, how these smaller pores and the bigger pores are arranged in the soil. Okay, in the soil. So this N is basically pore size distribution index, and this alpha is, we call it as the inverse of the reciprocal of the this thing. So knowing this theta, we can always compute the hydraulic conductivity, okay, which is equal to Ks. Ks is nothing but the saturated hydraulic conductivity multiplied by some fraction which depends upon the moisture content or the pressure. So if theta becomes theta r, what will happen to this? Zero. That means the hydraulic conductivity, unsaturated hydraulic conductivity becomes zero. So basically that they have introduced that parameter also, theta r. So we have 4 parameters which are required, okay, in unsaturated zone flow analysis. One is the porosity. Anyway, porosity we will be knowing. Theta r, the residual moisture content, then the alpha, okay, and n. These are the 4 parameters. Of course, the saturated hydraulic conductivity, Ks also. Ks, theta r, alpha, n, and phi. Okay, so these are the, so in addition to Ksat, if you see in saturated problems, so we are only we need only the saturated hydraulic conductivity. If it is unconfined aquifer, you will have specific yield. If you have a confined aquifer, you have storage coefficient. Okay, but here we need more parameters. The bubbling pressure, alpha, n, okay, theta r. Okay, so this is how. So this basically gives you the. Now let us go to, as I told you, okay, the hydraulic conductivity in the unsaturated flow modeling or flow analysis, we cannot take it as constant. There it is depends upon the moisture content or the pressure head, because we have a relationship between moisture content and pressure. Okay, so we can always get, so it depends upon the hydraulic conductivity, the measure of the ability of the soil to transmit water. So about the is as the saturated hydraulic conductivity if it is in the saturated zone, and for water contents below saturation, that means when the pressures are negative, it is referred as unsaturated hydraulic conductivity. Okay, so you can see how this is the variation of hydraulic conductivity with saturation. Okay, so see, at 100% saturation, you have what are the values or is equal to the saturated hydraulic conductivity. As the percentage saturation comes down, okay, so it will be decreasing. Okay, so and you will get, you can see the order of change. Okay, if you take you see take sand. Okay, it is around 10 around 5 centimeters per hour when it is fully saturated, but it has become almost 10 for minus 5 centimeters per hour as the saturation has gone by 18%. Okay, so there is a drastic decrease in the hydraulic conductivity as the soil becomes drier and drier. Okay, so now let us derive, okay, or let us see how we can analyze problems involving flow through unsaturated zone. Okay, so basically as any other equation, so we use the conservation laws to derive the governing equation. Okay, so the first is the continuity. Okay, we say that if I take a control volume, okay, whatever is the inflows and what are the outflows, the difference between the inflows and minus the outflow should be equal to the change in storage in the control volume. Okay, so if the inflows are more than outflows, there will be an increase in, okay, and if it is less, there will be a decrease in this. And this, how much this storage change will depend upon what type of soil we are using. Okay, isn't it? Okay, so the first is basically we use the Darcy's law. Here also we assume that the Darcy's law is valid. Okay, so the Darcy's law basically gives a linear relationship between the velocity and the hydraulic gradient. Okay, and this K here, okay, is what is K? K is the hydraulic conductivity. The only difference here is that in saturated zone, for a given soil, we take it K as constant, but whereas here K is not a constant, it's a function of the pressure gauge. So it is no more a constant. Okay? In Darcy's law, we use it. The only thing is here it becomes much more complicated, not complicated. So the K is pressure dependent or moisture content dependent rather than taking it as a constant. Okay, so then H is the hydraulic head, and here basically we have written it for vertical flow, and dH by dz is the vertical gradient. In mostly in unsaturated zone, the flow is mostly predominantly it is vertical because in vertical direction, in addition to pressure gradient, we also have gravity gradient. Okay, so that's why. So if I take a soil, unsaturated soil sample, if I put some water, okay, it will be flowing in vertical direction much more faster as compared to the spreading in horizontal direction. This is because you have the vertical gradients which will be facilitating flow downwards in addition to the pressure gradients. Okay, so here we have written it for the vertical flow. So my Q is equals to minus K into dH by dz. Okay,
It minus is plus here.
This one?
D of H minus Z.
Yeah, if you are taking Z direction vertically downwards, then it will be minus Z. If you are taking it positive upwards, it will be plus Z. Okay. So you can either way write it. Okay. So it depends upon how you take it. See, see here it's written that is elevation head taken positive pointing against gravity. That means basically. Okay. So so basically here this is the one actually minus k theta by dz into this is the pressure gradient. Okay. H is the pressure head which depends upon theta minus 1. Okay. So if I take, so that's why it is okay. So then we can write it this in terms of this, okay, combining Darcy's law. This D is called the soil moisture diffusivity, okay, which is defined as this K into dH by d theta, okay. Q is equals to minus d theta by dz into K by minus theta. So when you combine this Darcy's law with continuity equation, you get an equation like this. Basically, this is the governing equation of moisture movement, okay, in the unsaturated zone, okay, it with taking theta as the dependent variable, okay. Basically, whenever, see, how will the change in storage will be manifested in unsaturated zone? How do I know that there is some changes going on in the storage? Let us say I have a saturated soil sample with some moisture content. I have certain inflow and I have certain outflow. If inflow is more than outflow, what will happen to the soil sample? It is at, it will have, because some water will be stored in this, so the moisture content will increase. That means it becomes wetter. If it is, outflow is less than the inflow, it becomes dry. Isn't that means basically we want to see how the moisture content is changing. So my dependent variable is here theta. Okay. So how the moisture content is changing with this, we can solve this equation. Okay. To get, if I solve this, okay. So basically H is now a function of, or H of theta. Theta is a function of, what are the independent variables? Z and T. So I have to solve. If I solve this equation, I will get theta as a function of Z and T. Okay. Even though this, even though this equation 5, which we are showing, okay, is basically here the moisture content, the dependent variable is theta. Okay. But the main problem with this solving this in by making theta as a dependent variable is that this equation cannot be used for saturated regions. If the flow is, let us say I want to solve a problem which involves both saturated and unsaturated zones together. In such situations, we cannot use this because d theta, this soil moisture diffusivity in saturated zone, what will happen? In the saturated zone, because even though H is increasing, theta is not changing because in the saturated zone theta is constant. So this term dH by d theta becomes indeterminate. There is no change in theta, that means d theta is 0. So this d becomes indeterminate. So that's why we cannot use this the unsaturated flow equation with theta as a dependent variable in saturated regions. So we need to, if I want to use, then we have to convert this, or we have to express this in terms of the pressure head, Hs, because we know that H is, theta is a function of H. I can solve for H, and from that we can get what is theta. Okay. So to do that, we do this. We define one more. This C is for the soil moisture capacity or specific moisture capacity, which is equal to d theta by dh. Okay, ch is d theta by dh. Okay, so if I write it, then I can express my unsaturated flow equation in terms of h. Okay, rather than in terms of theta. If so, we solve this equation for h. So how do we get theta then? Let us say I solve this equation. So h is a function of z and t. So I solve this some way, okay, maybe analytically or numerically. Once I get h value here, how do I get the corresponding theta? So we have to use the the characteristic relationships like Van Gunnichen and all. Okay. So if you go back here, okay, this equation. Okay. So basically, if you see here, okay, I have got h. So knowing h and this parameter also should be known, theta or phi and alpha, that will be given to you. Okay. So if we are solving it, so theta r. So once you this, so I can know theta. Okay. So basically, you can solve this unsaturated flow equations in two ways, by considering the moisture content as the dependent variable or the pressure head as the dependent variable. But the limitation of this moisture content based equation is that it cannot be used for saturated regions. Okay, but whereas the pressure based equations can be used even for saturated regions. That means I can solve the entire saturated zone and the unsaturated zone together. There is no need to demarcate it. If I can solve, if I use the pressure bed head based, okay. But if you are using moisture content based, then it cannot be used. But the advantage of theta based equation is that this is much more mass conservative. Okay, especially if you are solving problems where you have steep fronts, like I have a very dry soil. I want to study the infiltration into this very dry soil. Okay. So if I want to use that, okay, if I want to solve the theta based relationship, okay, is much more accurate, okay, as compared to the h based equation. The main reason is that because if you see here, the curves, so here, if you see here, at very high negative pressures, that means very dry, okay, even though the pressures are varying widely, but the corresponding changes in the moisture content is not that much. Let us say minus 500 to minus 1000, but the corresponding change in theta will not be that much. Maybe it is 0.1 to 0.08 or something like that, especially in the dry zones. You have a very steep curve here. So this is the reason why the moisture content based solutions will be much more accurate, much more mass conservative as compared to the pressure head based equations. Okay, so you can solve either of them, and there are researchers who have mixed this too also. Okay, to get the advantages of both. So that is the beyond the scope of this lecture to go on. So basically, so we can solve this. So this equation, okay, is which we derive, okay, by combining the mass conservation equation with the Darcy's law, is called very well known. It is Richard's equation. Is the person who derived this in 1930s. Okay, and it has been widely used. Okay, for solving. So the main assumption here, what we have done here is that, as Professor Govindaraju said, that okay, the air which is present in the unsaturated, and we are taking that it is at atmospheric pressure, even though it is not current. Okay, so that makes this is the assumption which he has made, and this has been widely used, and there it's very useful, and in many practical applications the results which we get by solving this is very good. So this has been become very popular, and almost even now we all use wherever the unsaturated flow equation, especially the water resources people. Okay, so we use this equation for solving problems in. Okay, this equation. Okay. Even though this equation is, this is a nonlinear equation. Nonlinear is because we know that h is the dependent variable. Okay, to solve for h, we should know these constants, these coefficients k and c, which themselves are functions of h. So it makes this equation nonlinear. I am solving for h. So if I know these two are constants, it is easy. We can integrate it and get it. Or okay, but they themselves depend upon h. So we need to do some iterative technique. Okay, we have to do some value of h, find out kc, then integrate it. Okay, check whether what we are getting is matching with earlier and what we have assumed. If not, use the new one. So you have to go on doing iterations. Okay, to get this. Okay, so getting analytical solutions for this is quite tough. So we get analytical solutions for very simplified boundary conditions and all these things. So people, because wanted to simplify this, okay, with some simpler equations, okay. So basically, if I solve this equation, I can get the pressure head or the moisture content as a function of space and time. Okay. So in many cases, in many practical applications, we will be interested in having want to know what is happening at the ground surface. Let us say the soil is very dry, let us say rainfall has occurred. So I want to know how much is infiltrating. Okay, this is also a part of an unsaturated flow. So basically, you are giving water and it is entering the unsaturated zone. So if we have to solve, basically we have to solve this. But solving this itself involves, it is quite involved. So people think of getting some simplified solutions for what is happening at the ground surface. Okay, so the infiltration. What is infiltration? Infiltration is the process of water entering from the surface to the ground. Okay, so it is basically the phenomena which is occurring near the surface. Okay, of course, this is basically, if I want to solve this, I have to solve what is happening here. Okay, so people have started thinking whether we can come out with some simplified solution for solving locally this problem at the ground surface. Okay, so this is what the infiltration, okay, is the process of water entering the ground surface into the soil. Many factors in play. What are all the factors which will influence the infiltration? One is
Land cover.
okay. Let us take bare soil. Okay, land cover is there. Okay, let us say I have a bare soil. So one is how wet the soil is. If the soil is very wet, so the infiltration will be less because the soil doesn't have that much capacity to take. Okay, so the dryness of the soil. If it is very dry, it will take a lot of water. Okay, so basically, at what state this soil is. Okay, and how much water we are giving at the top. Okay. If the rate at which we are giving water is less than the capacity of this, it will take entire thing. But if it is more than that, it will take what it can, and the rest will go as surface runoff. So in surface runoff studies, okay, so this infiltration rate, getting the infiltration rate is a very important, okay, task. Okay, so there are many simplified. So the front which moves, okay, is called the wetting front. See, initially, let us say this is my soil is at this where it is very dry. So I put a water. Okay. So initially, the top portions will start getting getting wetter, and it moves. And if you see here, a typical after some time, if you see, this is what we get this. So the top portions are fully saturated. Okay, the middle portions are partially saturated, and here this is the wetting front. This is the tip of the wetting. So below this soil is very dry, and above this you have the effect of this infiltration. Okay, so if we want to get this curves, okay, or so we can simplify our governing equation, okay, to get the simplified solutions. Okay, so the infiltration rate is basically it will be changing with time, isn't it? Initially, the infiltration rate will be very high because the soil is very dry. As it becomes wetter, the infiltration rate becomes smaller and it reaches a steady state after some time. Okay, so we have to get basically, if I denote my infiltration rate by small f, okay, that is basically a function of t, isn't it? Okay, so if I want to know how much water has really gone in, okay, so I have to, this effect ft is what we call it as the cumulative infiltration, how much water has really entered, okay, because of since the starting, okay, will be the integral of this infiltration rate, okay, from 0 to t. And because this f is time varying, okay, so we have to, so basically if I have some idea of how this f is varying with t, okay, I can get how much is that, isn't it? So many people have tried to see how to get an expression for ft, the infiltration rate with respect to t. Okay, so the most important or the most widely used, I cannot say important, the widely used is the Horton's infiltration equation. It's a very simple equation, okay, and it is very well, it has been widely used, okay. What he said is f of t, okay, is equals to f naught plus f naught minus fc into e power minus kt, okay, where f naught is the initial infiltration rate, okay, I think when t is equal to 0, and fc is the final infiltration rate, okay, and k is a constant, okay, which depends upon the type of soil, okay. So e power minus kt. If you plot this curve, so it starts with f naught, okay, and it exponentially decreases and becomes fc for a very long time. Am I correct? F naught when kt is equals to 0, this f naught, this is fc.
Should be minus.
This should be fc. This should be fc. Sorry, there is a printing mistake. fc plus f naught minus fc into e power minus kt. When t becomes 0, okay, So when T becomes 0, so FC gets cancelled and you get F0, isn't it? So sorry, there is a printing mistake here. It should be FC. Am I correct, sir? Where K is the decay constant and it goes, okay? So basically, how many parameters we have here in this equation? We have FC, okay, which will become when this thing F0 and K, okay? Basically, if I have to use this Horton's equation, okay, so we need to do, we know that if I have a very dry soil, okay, and I infiltrated for an infinitely long time, what will be FC? What value it will reach? The soil has become fully saturated. Okay, so what will be the value of FC? At infinite time, will the water will keep on going or will it stop? It will stop. No, it will be going. It will be going with grade this FC,
Yes, it is.
isn't it? So that will be equal to, yes, hydraulic conductivity, saturated hydraulic conductivity of the soil. Whatever is extra will be moving on the surface, but it will be going with, it will not become 0, because we assume that the soil is infinitely big, okay? So FC will be equal to the hydraulic conductivity, the saturated hydraulic conductivity of the soil. F0, this K depends upon the type of soil, okay? If it is clay, it will have different Ks, okay? If it is sand, okay? And F0 also. F0 basically depends upon the dryness, at what dryness I am installing, okay? So this is one simple but quite widely used infiltration equation which we use. The other one is given by GIAN. Basically, the GIAN, they try to include some simple physics into the infiltration equation, okay? As compared to the Horton, okay? So what they assumed is that we know that as water moves into the soil, the front looks like this, okay? So there is a portion where it is fully saturated, then there is some partial saturations, and then you have the wetting front here. Okay, basically this is but what they assumed, this GIAN, is that the water moves like a piston. Okay, so what they have done is this transmission zone, no, they assume that it is straight line. That basically it is like a moving like a piston. Okay, so there is a sharp wetting front here. Up to here it is fully saturated, but here you have this much. Okay, so this is, even though this is an approximation, yes, the main advantage of assuming this is that we can get an analytical solution for our infiltration. Okay, so this is what we get. So basically, the wetting front, they have assumed that it is given in 1911, and it's even now it's widely used. Okay, especially in practical situations, is a very good alternative to the solution of Richard's equation. Okay, so the wetting front is a short boundary dividing soil moisture content below and the initial moisture content. This N is here, actually eta we use here is basically the porosity. Okay, and theta I is the initial moisture content. The wetting front has penetrated a length L, okay, in time t since the infiltration began. Water, and they have also assumed that the water is ponded. That means basically you are giving a continuous supply of water with constant head boundary at the top. That means I maintain this much of head throughout my experiment. Okay. There are two ways we can give. One is by maintaining this head or giving with some rate. Okay. But here they have used this. Okay. This is called the ponded boundary condition. Okay. So, and let us say in time t, okay, the moisture content has changed. Initially, the moisture content in the entire column is theta I, okay, and because of the infiltration, it has become eta. So the increase in the moisture content, the total amount of water which has gone in is nothing but L times L is the length multiplied by the increase in the moisture content in this, that is n minus eta minus theta, which we are showing it as delta theta, the change in the moisture content. Okay, so then this should be equal to, we know that water is moving here with certain this thing, so we apply Darcy's law here from up taking this point and this point. Okay, so the infiltration rate is given by this, F is equals to K into H1 minus H2 by Z1 minus Z2. Okay, so that we can write it as K is equals to psi plus L, where psi is the basically the pressure head here, L is the length of the column or length of the soil sample divided by the L is the length. So using this, we will get K is equals to F is equals to K psi theta, and we know that here what is here, you are able to see this, F is equals to dF by dt, where this capital F is the cumulative infiltration, how much has gone. Okay, so that is d, so df, the F, then the infiltration rate F will be dF by dt. So I replace this F by capital dF by dt is equals to K into psi del theta plus F by F. Okay, so when we solve this, so we basically we solve this for F. Once we get F, we can compute the small f. Basically, this involves what I can say is that you have to solve for cumulative infiltration. From there, you differentiate it. Basically, this cumulative infiltration will be a function of T. Okay. Once you get that, you differentiate that to get the infiltration rate at any time. Okay. So with the F is equals to K into psi del theta by F plus 1. That means F at any time is equals to K times psi del theta by F at that time plus 1. Okay. So I have given a few problems. Okay. When we solve this, we will be able to appreciate this. Okay. With much this thing. Okay. So now I will briefly talk about the parameter estimation. Of course, it's not been very fully this thing. So we know that now for solving problems in unsaturated zone, so we need the soil moisture characteristics. So to get the soil characteristics, I need the soil water retention parameters like alpha, N, theta, R. Okay. So how do we get there in laboratory or in the field? Okay. So this is what we call it as why. How do we estimate these parameters? Okay. So the soil water retention. Basically, the soil water retention parameters are nothing but this. basically this. Right. I want to know, let us say I want to know what is alpha and N for vanillation. Okay. So I need to take a soil sample. Okay. Let us say somebody gives you this soil and what are these alpha and N and what is theta R? What is the saturated hydraulic conductivity of this? Okay. So then only we will be able to solve the problems involving unsaturated fuel. So how do we get these parameters? Basically, there are two methods. Here I am just I will be telling only the direct methods. Okay. So actually we can estimate the parameters or we can get the parameters in two ways. One is directly by doing a laboratory or field experiments. Okay. To get these parameters. Okay. And other one is by indirect methods. Indirect methods are those in which uh, we measure the moisture contents, okay, for a given set of boundary conditions, and we can solve this by our analytical models, okay. So for those set of initial and boundary conditions, so we assume some values of these parameters, so we know what will be the moisture contents from our model, and we compare them with the experimental value, and we try to come out with these optimal parameters so that the difference between what we have measured and what this model gives becomes a minimum. It is very difficult for us to make it zero. It is impossible because of measurement errors, and also while deriving these equations also we have assumed certain assumptions. So that assumptions may not be fully valid during the experiments. Okay. So it is very difficult to get the difference between the measured and the model predicted moisture contents to zero. Okay. So we try to see that as much minimum as we can say. So and we take that as the parameter. So that is basically the indirect way of. But there are direct ways which are time consuming, but yes, they do have. So in this lecture, I will be talking only about the direct methods. Okay. So the main thing is the soil water retention parameters. Like how do we get the alpha and the N, the bubbling pressure, okay, and the N values. Okay. So one method is basically we do the experiments in. So this is the one which we use for measuring or for estimating alpha. This is what we call it as the pressure plate apparatus. Okay. This pressure plate apparatus, what we do is we take fully saturated soil sample. Okay. So we kept them in this. This is basically like a pressure chamber, or it is like a cooker. Okay. So and we keep these saturated soil samples in this containers, and we apply pressure. Okay. So then what will happen? Let us say I take a saturated soil sample, and if I apply pressure, what will happen? The water will come out because I am applying pressure. Okay. So the water will be coming out of this container. Okay. So when will the water stop? When this pressure is not unable to release further water from this, isn't it? So I just press this. Okay. Basically this is what. So I have a saturated sample. I press this. Okay. And I keep it like this. So water will come. Then it will stop till more water will come if I increase the pressure. But if I keep the same pressures, the water will stop. So at that time, whatever is the moisture content, so that will be equal to the corresponding to that pressure. So you know how much pressure you have applied. Okay. So when you apply the pressure, water will start coming out of this container and wait. After the water the coming of water has stopped. Take the sample. Will it be fully dry? No, it will not be dry. So you take that and find the moisture content. So for that moisture content, this is the pressure. Then take one more sample, fully saturated. Again, increase the pressure. Okay, let us say I have put 100 centimeters. Let me say 1000 centimeters. So then more water will come out because I am applying more pressure. What will happen to the corresponding moisture content? It will be much drier because it would have taken much more water from the sample, isn't it? Because I'm applying more pressure. Okay. So like this, for different pressure heads, we will be getting the different moisture contents. So I can plot it, isn't it? How moisture content is varying with pressure head. So with this, so once we get this data, okay, so basically we will be getting this data, this data point, okay, and try to fit the Van Gogh curve, okay, and whichever is the give, so and find out what is the corresponding values of alpha and V, alpha and N. Similarly, so how do we get porosity? You know, porosity is a standard laboratory method is there to get the porosity, and we also have for finding out the saturated hydraulic conductivity. How do we get it?
Constant rate and variation.
Huh? Yeah, in the laboratory, if you soil soil samples, we can use. I think even in your undergraduate, you would have done this. Okay, constant head permeameter or the falling head permeameter. Okay, so those can be used.
Field pumping test.
In the field, we don't use pumping tests. For unsaturated flow application, we use Gulev permeameter. Okay, so there is it's a very useful instrument. Okay, to get the saturated hydraulic conductivity in the field. Okay. So,
Sir, irradiance saturated.
huh?
Google parameter for saturated.
It gives saturated hydraulic. See, unsaturated hydraulic conductivity, it will be varying, isn't it? It cannot be a soil parameter. If I give a soil, given soil, I can have only Kn. Unsaturated hydraulic conductivity is a function of moisture content, so it cannot be a constant. Okay, so Bullock permeameter also, see unsaturated hydraulic conductivities you can do here. You will be getting a relationship between K and theta or K and H. Okay, there are many methods unsteady, and these methods are quite tough. Okay, so it's really if you have to. I have not yet done. I have done only the internal drainage experiments so far, but there are many methods. They require a lot of sophisticated equipment and all. Okay, so that's the this. So like steady flux methods. Okay, there are many methods. I think they're not really. So I think any questions? So I try to cover uh, the unsaturated zone, the basics, physics underlying this, and how do we solve some simple problems, okay, and the unsaturated zone modeling. Any questions, please? Basically, the contrast between saturated and unsaturated is that basically the manifestation in unsaturated zone is change in the moisture contents we observe. But whereas in saturated zones, we will be seeing how the pressure heads or the water table is changing, how the, okay. So the unsaturated zone, so how really the moisture content is, the state variable is moisture content here, whereas in saturated zones, it is either piezometric head or the water table elevations. Okay, so unsaturated zone is very important for soil physics, irrigation engineers. Okay, solute water transport. Okay, solute transport in unsaturated zones. Okay, so this so. Oh.
So bring their laptop because they're asking something. So
Laptops bring it, okay? So it will be fine, okay, sir?
yeah, I was just looking at the tutorial problems. Some of them require are asked you to plot a curve. So if you have a laptop, you can easily do that in Excel. So if you have laptops with you, you will benefit from bringing them today.
If you have laptops, if you do not have somebody, okay, you can always share, okay? So two of them together, okay? Whoever is having, please bring it, okay? So that it would be useful.